talk about what we're seeing in cloud, in particular around design, engineering, manufacturing, HPC applications. Talk a little bit about best practices, but really a Dougal Ballantyne session this morning, if you were able to catch it, went very deep into some methods of deployment on AWS. I'm going to talk a lot about use cases, what we're seeing out there across industries, pharmaceutical industries, engineering types of applications. And I don't just want to talk about HPC. HPC obviously is why you're here. It's why we're here. We care deeply about these applications, about providing scalability for HPC. But there are other factors that are leading enterprises, small manufacturers, research organizations into the cloud. Not just scalability of compute, but also things like globally collaborating on data, right? Securely accessing compute and data in a shared resource. Big data, although yes, it is definitely in the hype part of that cycle that Wolfgang mentioned earlier, or I'm sorry, it was mentioned earlier in the slides. Absolutely, big data is a big deal in the cloud. It drives a lot of compute, drives a lot of data storage. It is real out there. It is real in a lot of different industries and use cases. And it's absolutely helping to attract big compute cycles as well. I want to give one kind of very, very representative example of what we're seeing. Many AWS customers are kind of similar in their journey to the cloud, in their path to the cloud, as what I'll describe today. So HGST is a great example. So they're a global manufacturer. They're a disk drive manufacturer, enterprise class disk drives, really advanced stuff. Helium-filled drives is their latest innovation. They build disk drives for the highest scale storage appliances out there. HGST, this is actually originally the IBM disk drive division. It was sold at some point to Hitachi. Hitachi 2 years ago divested, sold HGST to Western Digital. As part of that divestiture, HGST went through this cycle of having to refresh their HPC infrastructure, their enterprise infrastructure, no longer had access to Hitachi's resources, didn't yet have access to Western Digital's. So they made a decision at that point to move to the cloud as much as possible, as fast as possible. And their story of how they've done that has been very enlightening for other customers in the manufacturing sector. They started with some compelling use cases in HPC, doing things like molecular modeling simulations, other simulations, working with ISV partners to onboard onto the cloud. They also started to do a lot more with big data, in particular get data from the manufacturing facilities into the cloud, into a shared data platform that they built in the cloud on AWS, and then use that to inform their simulations, to close the loop between quality analytics in the manufacturing side, yield analytics, and then the engineering simulation. So it's a really compelling set of use cases, kind of a great story for other enterprises that are in a similar kind of refresh mode. I'll talk about other use cases in a few moments that we're seeing across industries. The important thing to understand about the cloud, certainly about AWS, is that it's not just kind of computers for rent. It's not just infrastructure as a service. All of the cloud providers, certainly AWS, provide platform services, managed services above and beyond what you see there. If you were at Dougal's talk this morning, you saw mention of things like simple queuing service, DynamoDB, CloudFormation, autoscaling. All of these are services that are layered on top of the fundamental cloud services that are offered. I'll talk a bit later about things like workspaces, which is remote desktops in the cloud. AWS is global, as I'm sure you know. We've got regions around the world. We're growing very, very fast. These regions, and those are the orange boxes here, all consist of multiple availability zones, as we call them, each of which is one or more, usually a cluster of data centers. And that provides, even within a single region, high availability, redundancy for compliance and an availability sensitive applications. It's also important to know that if you choose to deploy in one particular region, like the US West or the EU, we don't move your data out. You're deployed in that region, you know exactly where it is. And for compliance reasons, that's very, very important. Also talk about EC2, Elastic Compute Cloud. Since its beginnings back in 2006, 2007, we've just continued to add new instance types, new virtual servers. And if we move to the right of this list to today, we see a huge number of individual instance types that allow you to have access to the latest generation Intel CPUs, Ivy Bridge-based servers, for example. We're very transparent about what you're getting in those servers. We're not oversubscribing. We provide access to things like AVX. So if you're developing high-performance applications that rely on very close to the metal performance, you can get that on AWS with the latest generation instance types. A really important aspect of HPC in the cloud is the ability to right-size the clusters, right? So if you're running Monte Carlo simulations that are just CPU intensive, use instance types that are kind of more on the ratio of CPU versus RAM. If you're doing in-memory databases, pick instance types that have lots of RAM relative to the CPU. If you need lots of local SSD storage and scratch storage, there's other instance types for that. So the idea here is that you can not only scale out that kind of grid environment within the cloud, you can also think about scaling up, right? So scale up with more memory, scale up with more CPUs in the box, more cores, or scale down. Scale down is incredibly important, right? So if you scale up a cluster, run your job, you should be able to scale it back down when you're done quickly and not pay for it. So that idea that you scale up, scale out, scale down, incredibly important concept in the cloud. It makes managing HPC applications in the cloud a really different proposition from managing them in fixed infrastructure. Important aspect of this is automation. And again, we saw this morning, if you were in a Google session, how automation can help you to set up programmatically methods of scaling up, scaling down, using things like triggers. If you have a job queue using a job scheduler, have the job queue automatically trigger an auto-scaling event, so it'll add more servers as the number of jobs in the queue gets deeper. Adding to that, perhaps, a more complex scheduler that will pre-stage the data where you need it, right? Or that'll spin up different types of instances for different applications. And all of that automation is possible using the tooling that's provided now on AWS. As you extend this idea into the hybrid cloud, you can now think about creating automation that extends not only in your own infrastructure, not only in the cloud, in your virtual private cloud, but also back to your local infrastructure. So if you're using job management tools, if you're using tools for data management, you can now spread those tools between your on-premise infrastructure and the cloud, creating this hybrid environment. You can do that either over the public internet using VPNs, or you can set up something like a direct connect. We have a service allowing you to create a private connection with a third-party partner from your data center into AWS, not crossing the public internet. This is common now for large enterprises, government agencies, to create these private connections into a virtual private cloud on AWS to extend their data centers, their subnets, their applications into the cloud. Again, automation is very important. The traditional tools for HPC, whether you're using Adaptive MOAB, you're using other third-party tools to manage your HPC infrastructure, those can also be extended now into the cloud. Virtually any job scheduler you can think of, Torque, Slurm, OpenLava, right? Condor, all can be run on the cloud now, just as you would in your own infrastructure. The primary difference, as I mentioned earlier, is that you can scale up and scale down that infrastructure. So rather than managing a fixed size cluster at relatively low utilization, you can now have the cluster grow and shrink according to demand. There's also, think of them as second generation tools now that are born in the cloud, that are really designed around that scalability of the cloud. Partners that we have, such as Cycle Computing, build infrastructure that allow you to automatically scale up, scale down using things like our spot instances. Spot instances are an interesting model where you bid for available capacity, you pay very little. When that capacity is available and cheap, you run your jobs. If the capacity is not there in the spot instances, the price has gone up too much, don't run your jobs, delay them. Partners like Cycle Computing or tools that you can build yourself for automation can help you take great advantage of things like SPA on AWS. MIT Star Cluster also can take advantage of SPA, help you scale up and scale down. We saw earlier today how CloudFormation, how auto-scaling can be used with higher level tools like the CFN cluster template that Dougal showed. CFN cluster is publicly available. You can grab it off GitHub. It's a great way to get started with automation on AWS. You can extend that as you need. We provide all the source code for it. Let's talk now about some of the use cases that we're seeing on AWS, and I've got a lot. I'm going to bang through them fairly fast here. This one I particularly like because it represents what we often see as the first use of cloud HPC in enterprise customers. Shadow IT is what some would call this. So you've got a guy off in the department, in this case Alex Gorovich at Cypress Semiconductor, who has an engineering challenge. He's designing the next generation touchscreen controller that's going to go into any number of different devices. He needs to do capacitance simulations, multi-physics simulations, to simulate finger motions and temperatures and all of these things that go into accuracy in your touchscreen sensors. Well, because he's a forward-looking project, he doesn't have high priority, he can't seem to get enough time in the job queue, right? So he submits jobs, they're run in parallel, they're in amongst all the other jobs in the centrally managed cluster. It takes him a week, 2 weeks to get through all of his parameter sweeps and get that result back, right? So he says, well, what if I use the cloud, right? So he actually came to one of our events in San Francisco last year, spoke to a solutions architect, did a little whiteboard diagramming, and he had the aha moment that he could actually run all of those parameter sweeps in parallel and not through the job queue in that central IT department. So he just ran a credit card and started doing it. I'm not sure he asked permission of the ISVs that were involved, in this case Comsol, or of his management at Cypress. But soon they got wind of it. We talked to the ISV, everyone was okay with it, and he was off to the races. And now he's able to run these simulations in a matter of hours rather than waiting a week, 2 weeks for them all to get through the job queues. So this is what we see it again and again in terms of accelerating innovation in engineering. Those first attempts, those first shadow IT projects become formalized, become accepted, and it just moves up the chain until it's an accepted method of engineering in these organizations. We also see innovative new startups in the HPC space. Great example is stochastic simulation down in Australia. They're working with oil and gas majors in the off the coast of Western Australia to do these reservoir sims. And as you may know, reservoir simulation is computationally intensive, it's data intensive, it involves data that's protected and highly proprietary. They use our Australia region. They create this business, ResAssure is their product, and they're serving customers, again, in the majors in the oil and gas industry in Australia in an entirely cloud-based solution for reservoir simulation. We're seeing quite a lot in pharmaceuticals. In fact, pharmaceutical industry was one of the earliest adopters of cloud at scale for things like doing protein docking problems, molecular dynamics for drug discovery. You've seen quite a bit of press around some of the large runs that we've done in that area. 50,000 cores was mentioned earlier, and that's a sort of a normal size now for these runs. We've seen much larger. In this case, a relatively small problem. They had an on-premise, a couple of servers they were using to do this analysis of clinical trials data. They moved that into the cloud. They parallelized it to 256 servers. They can run that on demand, short periods of time, get the answers turned around much, much faster, right? So 1.2 hours versus 60 in the past. Now, from an HPC perspective, that's a relatively small number of cores. As I said, we're seeing much, much larger. The critical thing about this is critical sensitive data, compliance sensitive data. They've got to be compliant with, whether it's HIPAA or FDA or other regimens. The pharmaceutical industries, healthcare, genomics, as that moves into clinical relevance, that security and compliance is very, very important, and it's well supported on AWS. Illumina is another example. So Illumina has created this product called BaseSpace. Base space allows you to stream the data that's coming off the genomic sequencers straight up into a cloud-based platform where they can do the secondary analysis on that data. What's particularly interesting about Base Space is it's also a platform for their partners. So if you're a partner of Illumina, maybe providing some innovative variance detection algorithm or something that's a big data oriented, you can now collaborate with Illumina in the cloud, create your business, and attach it to the customer's data in this secure environment. In the case of Illumina, what they've chosen to do is publish a best practices security white paper that their partners and their customers use to verify that they are remaining completely compliant, they're using security best practices to secure that data in the cloud, to collaborate on it in a secure way. Data encrypted in flight and at rest and so forth. What are the various security models that are needed to, for example, to remain compliant with HIPAA or other regimens. Pfizer, yet another example. They do quite a lot of work with us now in the cloud for these molecular modeling problems, protein problems. They have specifically told us that the security and compliance that they get on AWS is perfectly adequate, more than they need, in fact, for these molecular modeling problems. And we're hearing that from other organizations, Novartis, for example, making use of AWS now for these drug discovery runs at high scale. I want to shift and talk a little bit now about that second topic I mentioned, collaboration in the cloud. We're hearing this from organizations such as GE. We're hearing it from organizations such as HGST, who have globally distributed engineering teams. We're hearing it in semiconductor, for example. Teams in Europe, teams in Asia, teams in the US that need to collaborate securely on this data. Using remote login, whether it's to a locally replicated virtual data center in your region, or collaborating globally on a single shared environment in the cloud, has proven to be highly effective for these organizations. Don't ship the data all around the planet. Don't push compute all over the place. Don't send servers in boxes to your remote teams. Keep it all in one place. Keep the data there, and just push pixels. Right? That's the end goal. Now, in reality, latency can be a concern if it's an interactive application. There's absolutely solutions now that help with this. Whether it's remote login applications like nice DCV, I think we'll hear about later today, that are with GPU acceleration on the server side, which we offer, as a great solution for that. And the key message, what we're hearing from many of our enterprise customers, is they're now viewing cloud collaboration as being more secure than what they can do themselves, certainly if they're distributed with data centers and data closets all over the planet. Much more secure to keep the data, keep the compute in one place, in the cloud, build automation, build security around it, monitor everything, put audit trails in place, and make sure that that data is secure. And again, just push the pixels to the end users. And you can do this, again, as I said, by centralizing the data in one place, centralizing the compute, or you can think about a multi-region strategy where you're replicating data in other regions, still in the cloud, but localized to the specific region where it will be accessed. Or if you have geo-protected data, as is the case in seismic, choose your region accordingly. I borrowed some imagery from the NICE folks here, so thank you for providing that earlier. But NICE DCV is a great example of a tool that can be used to provide a remote login experience to your private data center or to the cloud very effectively. And NICE can take advantage of our GPU instances. We've got NVIDIA GPUs in our G2 instance types, and NICE DCV takes very nice advantage of those for doing remote 3D graphics, as you may see. We also have Amazon Workspaces. So if you just want to have managed Windows desktops in the cloud, Amazon Workspaces is a great solution for that. Amazon Workspaces is an environment where you can share your Windows desktop, you can access your Windows desktop from thin clients, from iPads, from various types of devices. You can also have a central IT team manage these Windows desktops, manage the patch levels of the applications, hook into their local Active Directory, whatever is needed from a central management perspective for globally distributed teams. So lots and lots happening now in this remote desktop, remote collaboration types of environments. Much of it driven not by HPC, of course, but by the needs of large enterprises that are beginning to see that remote desktop, virtual desktop is a very effective strategy, not only for their own data centers, but in their cloud applications as well. We're seeing a lot of innovation around this. So in the area of, say, medical imaging, companies like Calgary Scientific have been providing GPU-accelerated shims, if you will, or libraries that can be used to take existing applications and to modify them for remote visualization applications. Calgary Scientific has now moved into things like engineering CAD applications, into seismic. They're doing lots of work on AWS with our G2 instance types. We also have our own offering, AppStream. So AppStream is yet another way that you can access GPUs in the cloud. AppStream was really designed to support streaming games, to support streaming video types of applications, but it can also be used for interactive applications. And a number of ISVs out there are looking at AppStream with interest and are beginning to deploy some aspects of their applications, the remote visualization aspects, using AppStream. Last thing I want to mention again is this big data. So big data has been a huge driver of compute on AWS from day one. I mean, big data was really one of the motivators for us to create cloud services and to require these kinds of services ourselves at Amazon.com. Because Amazon.com has always been about big data, enormous numbers of transactions, sensitive data for consumers, pushing things like recommendation engines and so forth. Those are big data challenges. And they may not sound compelling from sort of a scientific and research perspective, trying to figure out which ad to push to you, when you're surfing the web. But that's a huge, huge business. And it drives a lot of innovation that can then be used by organizations like FINRA in the financial sector, now on AWS, DNA Nexus in the genomics side, big data for life sciences, and others. So thank you. That was 45 minutes of material and hopefully 20 or so. But a lot happening on AWS. Thank you all for listening. I can take questions if there's time.
Sure, thank you very much.